Okay, so welcome everybody. It is my pleasure to introduce Joonas Turunen from University of Vienna. Joonas did his PhD in University of Helsinki. He then worked at INS Lyon in LabEx Lyon and is now a postdoc in University of Vienna. As I said, his contribution is entitled Statistical Mechanics Models on Random Maps of the Disk and the Half Plane. Please, Joonas, go ahead.
All right, thank you, Matteo, for the introduction, and thanks for the kind invitation to give a talk in this seminar. And so, as Matteo mentioned, I'm going to talk about statistical mechanics models on random maps in disk topology and the half-plane limit, which we can obtain from that. And this is mostly based on my joint works with Linxiao Chen, who is now working at Paris 13, Paris Nord, and also a tiny bit on my own paper. And all right, so let me get started. So let me recall a bit background about the Ising model. So it's one of those canonical models of ferromagnetism in statistical mechanics, and in some sense, it's a simple toy model of it. And it's also one of the most popular statistical mechanics lattice models because it's exactly solvable and in some sense non-trivial. So for example, compared to percolation, it has more structure. And usually it's defined on a fixed graph. Well, that model was introduced by Lenz in 1920, and it was solved by his PhD student Ising in 1 dimensions a few years later. And it has been generalized to higher dimensions since then, but most of the interesting results have been proven in 2 dimensions. So some remarkable properties in 2 dimensions. Well, first in 1944, Onsager was able to show the model exactly in the physics sense, and also found a phase transition, which didn't hold for 1 dimension. Well, later on, there were many developments, but in the 80s, there were these physicists Belavin, Polyakov, and Chamolochikov, who basically studied conformal field theory, and that time it was realized that the Ising model corresponds to a conformal field theory. So there's a lot of tools from that side. Well, and then more modern thing is to study those interfaces and how their geometric structure scale when you make the lattice mesh smaller. And then that led those remarkable discoveries about conformal invariant scaling limits, which correspond to SLE corridors. All right, and that's Stas Smirnov is one example, and he was awarded Fields Medal from various things related to this type of thing. Okay, so let me define this Ising model on a fixed graph. So let us consider a finite graph G with its usual vertex and edge sets. And the spin configuration, we assigned it to vertices. So we either put a minus spin or a plus spin to each of the vertex of the graph. Okay, so this is just putting formally a number -1 or +1. Well, then we can define a probability measure on spin configurations. Since we have a finite graph, we have finite number of spin configurations, so we can just define it by looking at so-called Boltzmann weight, where we introduce a non-negative parameter beta, and then we just exponentiate beta times spins in a neighboring vertices. So that is, we look at an edge, and then we look at the spins on the endpoint of edge, multiply them to each other. So, okay, so this measure really favors spins to be same, at least when beta is correctly chosen. So it's a natural measure in spin configurations. And so this measure is generally a Boltzmann measure, and this beta parameter is called an inverse temperature. Well, in order to make this a probability measure, we need to renormalize this product of Boltzmann weights by a partition function where we simply just sum over all the spin configurations, and the number of them is finite if the graph is finite. All right. So, but we can also reformulate this by introducing a different weight nu, where we actually count the number of edges which share the same spins at endpoints. So we call that type of edges monochromatic. So then it holds that positive betas correspond to nus greater than 1. And we call the model ferromagnetic in this regime. And this is the regime we are studying in this talk. Okay. So let me give you an example in a picture. So we are talking about 2 dimensions, and we embed a graph, planar graph. So planar graph is a graph which has an embedding to plane, and now this picture shows actually the embedding. So it means that basically edges cannot cross with each other, and also we can topologically deform this on the plane without changing the graph. Okay. Well, then we add the spin configuration. So in each vertex of the graph, we put either -1 or +1. So I just call them minus or plus. And naturally, if you like a more combinatorial approach, maybe you might prefer to think about colors. So we can have a color code for those spins. Well, then we have here an external phase. So it's a triangulation of a disk. So all the faces have degree 3. And then we have also marked an edge on the boundary, which we call rho, and that would be a root edge. Then there's opposite row dagger edge, and then there's a boundary condition between those edges. So this is something I'm going to talk slightly more later. But now let me move on this fixed graph setting to a random graph setting, or more like random lattice. Okay, so how about if we study Ising model on random so-called dynamical lattices? So this dates back to the physics in the 80s. So there were Kazakov and Bulatov who introduced this model and studied it. First, Kazakov studied it on quadrangulations, and later on with Bulatov, he continued to study it on the triangulations. And they also found a phase transition, similarly as in the 2D Ising model on regular lattices. Well, what are the physics motivations to study this? Well, in the 80s, there was also interest in this Liouville quantum gravity coupled with matter. So Polyakov introduced this in 1981 as a model of string, basically. And so it was kind of expected that this Ising model on dynamical lattices would be a discretization of this Liouville quantum gravity with certain matter fields. Well, another motivation is that there was also relation by Kitniks, Polyakov, and Zamolodchikov, which relate the critical scaling exponents in the quantum gravity setting to Euclidean setting. So that would provide a link between random lattices and regular lattices. So that's also something which motivates the study on random lattices, because many times those critical exponents are in fact easier to compute in the quantum side. Okay, so that physics works by Kazakov and Bulatov already reveal like different critical behavior compared to the pure gravity universe class, which means that we are looking at random lattices without any matter field. But in the language of modern math, like we are talking about random planar maps coupled with an annealed Ising model. And I'm going to shortly introduce what this all about. Well, but what we really want to do, we want to find a critical behavior of a model which differs from the pure gravity. So pure gravity in math language means a universal class of the Brownian map. So, and we would see how this different critical behavior also reflects the geometry of the lattice. All right, so that's all about the motivation. Let me go to the definitions. So first, what is a planar map? So it's simply a connected graph or multigraph properly embedded in a sphere, two-dimensional sphere, where we take it modulo orientation preserving homeomorphisms of the sphere. So it just means that we cannot we can only topologically deform the graph on the sphere such that no edges cross with each other, more or less. Okay, so then we distinguish an oriented edge or corner in the map, which we call the root. And this is simply by combinatorial purposes. Well, we also distinguish a face, which is, say, on the right of the root edge, and that we call an external face. And the rooted map is called a triangulation if all the faces are triangles, and it's a triangulation of a simple m-gon if it has an external face, which is a simple polygon of length m. And simple means it doesn't have pinch points on the boundary. So here are two examples of planar maps, which actually, as planar graphs, they're the same, but they're embedded in a different way. And as you see here on the left-hand side, you cannot really deform this edge such that it would become the same map as this. So there are clearly two different maps. And now you can see also that this map here is a triangulation of the full plane, because both of these faces have degree 3. So this edge you count twice, you go around it, and then here, so it has perimeter 3, this face. And same is on this side. Okay, well, this is not the triangulation. Okay, well, let me now introduce the model, Ising model on these maps. So how do we do it? So we add to each internal face, which is a triangle, a spin, either plus or minus. Or alternatively, we can do this for vertices. And then we assign so-called Dobrushin boundary condition, which means that we fix the spins at the boundary. Well, if the spins are on vertices, this is kind of simple. We just put all of those vertices adjacent to the boundary. We put spins plus or minus in a sequence where we have, let's say, p pluses first between row and row dagger, and then we have q minuses. And we can say that, okay, we do it counterclockwise from the root. Okay, we can do the same when the spins are on faces, but at that point we need to just make a convention that we assign the spins outside the edge. So we could imagine that there are some external face here or some external triangles which carry this spin. Okay. So this is purely combinatorial what I'm talking about. I'm not talking about probability distributions yet. Okay. So let me then mention that or define what's the notion of volume. So we want to somehow measure the size of a triangulation. So if the spins are on the faces, it's more convenient to use the number of faces as a volume. Okay, so this is F will be the face set and this number of faces. Or we can also say a number of edges when the spins are on vertices. And we denote a spin configuration by sigma as usual. And we call an edge monochromatic if it separates either two faces with the same spin or two vertices with the same spin, depending what model we are talking about. So here is an example picture of a model where spins are on faces. So I use this color code here. And so I called by E T sigma the set of monochromatic edges in a triangulation T sigma. So here, like monochromatic edges are represented by those dashed lines. And we can count that, okay, in this picture, there are 18 monochromatic edges. And observe that those edges, they take into account the boundary. So we also count boundary edges which are monochromatic. And that's important because we want the boundary conditions somehow affect the probability distribution. Okay, well, on the left-hand side, we have the same map without any decoration. So it's just like a triangulation. And in this time, we have rooted at the corner here. So let's say that we can root edge could be this first plus edge on the right, for example. well, it has 19 faces. We also want to keep track on the volume. And we prohibit all the pinch points on the boundary. Okay. So I hope the model is more or less clear now. So I will go on to the probabilistic side, but before that, let me define a partition function. So eventually I want to normalize Boltzmann weights, which are here, to probability distribution. So that's why I define a partition function. So the idea is that I fix the boundary length of the polygon to be p plus q, where we have p plus spins and q minus spins. And then we have a Dobrushin boundary condition in this way. And then we look at all the possible triangulations with spin configuration with this boundary condition. Okay, so we just define formally the partition function by introducing two parameters t and nu, where t now counts the volume of the map and nu counts the number of monochromatic edges of the map. Okay, well, how to understand this? So this is purely combinatorial. This is a formal series, and we want to understand how does this behave when p and q are large, and let's say t and u are sufficiently small so that it's finite. So in order to do this, we write a generating function for them, which is, again, it's a formal power series, where this zpq here is just a coefficient, and then we have two variables u and v. So u is now variable which takes into account the plus boundary length, and v takes into account the minus boundary length. Okay. So what is the motivation here? That to study this type of object, we would like to apply analytic combinatorics. And we would like to understand basically the singularity structure of this generating function. So first of all, we need to find an expression for it. And then we would like to study the regime where it's analytic, and then find the singularities of it. Okay. So that's the motivation. So first theorem, we are talking about spins on faces, but something similar works for spins on vertices as well. So if we now fix a temperature nu greater than 1, we can actually show that this generating function is algebraic, and moreover, it has an explicit expression via a rational parametrization. So what does it really mean? It means that there exist three rational functions, t hat, u hat, and z hat, such that z can be expressed as z hat with a change of variable, where now t, or say t squared, is given by a rational function t hat, and u is given by t times u is given by a rational function u hat, and then t times v is given by the same rational function u, but just evaluated at different point. Okay, so this is simply a change of variable or reparametrization, which gives us an explicit expression, and this is something we can really compute. Okay. So what does this theorem basically indicate if we are thinking about the physics of the model? So it means that the Ising model on random triangulation should be exactly solvable. So it means that we can compute many observables, for example, the free energy in many scaling limits. Okay. Very good. So we have an explicit expression. So it's not an exact solution of z itself, like in the usual sense, but it's a reparametrization. Well, but we can do many things with this. So how do we prove this? So the idea is that we make a decomposition of a map with fixed boundary length. So we look at first a triangulation of a disk with, let's say, at least one plus edge on the boundary. And the plus boundary length is p plus 1 and minus boundary length is q. So how can we decompose it? We can always look at the first triangle, which is, or the triangle which is adjacent to this edge, well, or incident to this edge. Well, that one, if it exists, it has several possibilities. First of all, it can have spin plus or it can have spin minus. Okay, so we need to look at all those cases. And then the third vertex, it could lie either inside the triangulation or it could lie on the boundary. So we need to also look at those different cases. Okay, well, here, in this picture, we have the spins on faces. So there could be some cases, for example, here that this is counted twice. So if we look at it belongs to both plus and minus boundary, then we just subtract it. We do the same for the opposite spin. And then we also consider the trivial cases where there's no or let's say not trivial, but pathological cases where there's no internal triangle. So, okay. But the idea here is that if we reveal a plus triangle, then it would also erase one monochromatic edge at the boundary, and it would also erase one face. So then there's a new unexplored map here, which has one less face and one less or monochromatic edge. Okay. All right. So here in the minus spin, there's like a anti-symmetry because here there is no monochromatic edge erased. So this edge is not monochromatic. That's why there's no parameter nu. Okay. Well, we can turn this into an equation. So we simply it's a recursive decomposition. So here we just increase the plus boundary by 1 here in this picture. And here we just sum over the different locations of this third vertex of the triangle, which is revealed. Okay. And all right, so this picture is more useful for intuition than this formula. But anyhow, what is now kind of what we want to do is that we want to study the generating function of this. So that's why we just sum over p's and q's and we weight it by the terms u to the power p and v to the power q. So we find a system of equations for generating function z u v. And this system, it's simply we just exchange u and v. We find a system which miraculously, because here we have the anti-symmetry between plus and minus edge because of this choice of revealing always from plus edge, we find two equations which are not independent from each other. So then it turns out that this system we can actually solve pretty well. So it's sort of like a discrete differential equation system. And we just apply usual tricks. So we extract coefficients out, for example, to find like simpler equations. And we could actually eliminate this z1 here, which is now we just condition minus boundary to be of length 1. Okay, so we can eliminate it. So we find an expression, explicit expression, which now depends on u, v, and some generating functions z0, u, and z0, v. Okay, well, what is this z0? It's just simply the generating function of a map with a monochromatic boundary. So it means that we have here only either plus boundary or minus boundary. So in this picture, we would have only pluses on the boundary. And that's something which is unknown. So we have a rational expression, but this z0 is unknown at this point. But as a side product, we also get another functional equation of z0, which now depends on z1 and z3, which are now simply partition functions for Ising triangulations with really small boundaries. So 1 is one plus bin on the boundary and 3 is 3 plus bins on the boundary. Okay, well, we are kind of lucky because this has been studied in the literature before. So there's a work by Olivier Bernardi and Mireille Bousquet-Melot where they found explicit parametric expressions for this z1 and z3 here, together with t, which is now, I recall, is the variable for the volume. Well, we can plug them in and apply computer algebra to find an explicit rational parameterization for u and this z0u for any given nu. Okay. So this one is kind of nice because then we just plug this parameterization in here and we get the explicit expression. it's not exactly this easy, because for general nu, the computation time would run out. So we need to find some, let's say, sequence of news with real concrete values, such that we find the explicit things, and then we use interpolation techniques to kind of guess a correct solution, and then a posteriori we can check that the correct solutions is indeed a solution for this. Okay. Well, Bernardin and Busquet-Mellon also showed that when we look at the partition function of Ising triangulation with a small boundary, it has this type of critical behavior. So there is a critical value of nu, which I recall is a temperature parameter, such that it has a parallel tail with exponent -7/3. Well, when temperature is not critical, there's exponent -5/2, and this is something which is well known in pure gravity when we look at planar maps without any decoration of statistical mechanics model. Okay, and this gives us a function actually of a critical line, which we can rather directly apply to our model. So we find a critical line and a unique critical point on the line at which a phase transition should occur. And what is this TC, which depends on temperature nu, and it's this tau nu here. So it's simply the radius of convergence of this viewed as a formal series in T for any fixed nu. Okay, so kind of what we just did was that we applied previous combinatorial literature to find exactly a critical point and a critical line. Okay, so let us study our model on this critical line from now on. So what is first theorem about this is that if we fix a temperature, we find an asymptotic expression for this ZPQ. So, okay, in the title, I mentioned that I also want to study using the triangulations of the half plane. So how to get to the half plane is that we want to let P and Q tend to infinity. So we want to have an infinite boundary. So to find these asymptotics, we apply basically analytic combinatorics to the generating function big Z of variables U and V. To do this, after doing this, we find asymptotics, set of asymptotics with a set of critical exponents. And let me explain a bit what's going on here. So assume now that we are, let's say, in the high temperature regime. Then here we would have the critical exponent for this minus boundary length to be 5/2. This alpha 0 plus 1 is equal to 5/2 if this alpha 0 is 2/2. And this is already found many times in pure gravity or Brownian map university class. So it's well predicted. And the same should happen also in the low temperature, which is indeed true. Well, this is only when we look at one boundary segment. So then we can also, there will be then a constant which depends on the remaining boundary length. So there's still a plus boundary present. Well, this has slightly different asymptotics here. And this I won't explain in detail, but this exponent alpha 1 differs in all of these three regimes. And the reason why it is that, well, it really defines a different kind of geometric behavior. So either low temperature or high temperature, the model should have a different behavior. And same in the critical temperature, okay? Well, but we can also bypass this two-step limit by letting the P and Q tend to infinity simultaneously. So that is, we let the plus and minus boundary tend to infinity same time at some rate, which is, well, this is more technical condition that we need a ratio of these two boundary lengths to stay on a interval, like closed interval, which doesn't include 0 or infinity. Okay. So we want this to stay controlled somehow. But anyway, so we find asymptotics with a slightly different critical exponent, which is also slightly different in the high and low temperature cases. And by a kind of looks like a coincidence, looks like not a coincidence actually, that this alpha 0 is sum of alpha 0, alpha 2 is a sum of alpha 0 and alpha 1, but actually it's not really clear why this is the case. So actually this constant here won't be obtained as a sum of this, but it's more complicated. Okay, well, but anyway, we have a good set of asymptotics for this, which basically gives us the key to study this model probabilistically. So we could define the Boltzmann distribution and study limit distributions of this. Well, let me anyway give a few words about the proof of this. So what is the idea is that in order to apply analytic combinatorics, we would like to understand the singularity structure of this Z generating function. And since we found the explicit expression via rational parametrization, it boils down to understand the singularity structure of the rational parametrization itself. So here we also parameterize the critical line with the parameter S. So it's also new hat is a rational function. So what does this procedure really involve? So first we should identify a dominant singularity of this generating function Z. So how is it done? We basically look at the critical points of this U hat, and we show that U hat actually defines a conformal bijection between the domains around origin where this Z and this Z hat converge. So they are defined both in the complex plane, but they have different domains of convergence. Okay. Well, then we show that this UC nu is a unique dominant singularity of Z. So that's really non-trivial thing to do and takes a lot of effort. So a particular step is that we show that this rational function Z hat has only one pole, which is mapped to the boundary point UC nu in for both of those variables U and B. So then it would be like the product of those disks, and it would be a boundary point on those, and it would be exactly the same point. So U and V are clearly symmetric in this generating function. Okay. So finally, we deduce that this function Z is actually holomorphic or analytic in a product of delta domains. And delta domain, I would show in the next slide what it means. So this really very roughly means that it's amenable to those transfer theorems of analytic combinatorics, which are very familiar from the book of Flageolet and Zetkevich. Okay. So here are some pictures. So delta domain would be here in the picture A. It would be this domain with the green boundary curve here. So it looks like a camembert. And we could show that actually, if we now rescale the Z UV to be convergent in a unique disk, then at the boundary of the disk, there would be a unique singularity, let's say UC. And we could, in fact, extend Z analytically to a larger domain. In some case, we can even find a slit disk where this delta domain has an angle 0. Okay. And how does it look on the rational parametric side? So it depends slightly on the temperature, but at least this this disk is an image of this kind of drop, like water drop shaped domain around origin, and it has the corresponding parameter of H here, which now maps to the singularity, dominant singularity. Okay. Well, this B and C, there are two different pictures, because the C is how we can extend this domain of analyticity at critical temperature, and this B is how we can do it in non-critical temperature. And actually here we could have it slightly larger, so we see that the angle here of this blue curve is slightly larger in the non-critical temperature, but I won't go to details. This is something which explains a bit like why the critical exponents are different in critical and non-critical temperatures. Okay, well, but then once we understand this Turnitin function and how it's what is singularity structure, we can expand it around the dominant singularity. So it will be analytic, except at the dominant singularity and a slit here, for example. So then we just expand it and we use Cauchy integral formula to find asymptotics of this ZBQ. So that's a rough idea. And yeah, so I mentioned already that these domains here look different for different temperatures. So hence we would get different local expansions, well, with different critical exponents. And this tells us, shows us a phase transition in a combinatorial level. So this is only combinatorics. Okay, well, let's move on to the probability and see how this phase transition is seen there. So I remind you what is our setting. So this is, we are considering spins on faces or on the vertices. So okay, in this picture they are in faces, and then we need to keep track of the volume, and we need to keep track on the number of monochromatic edges. But since we are interested in the half plane, and we want to study probability distributions which depend on the boundary length, well, in the fixed case, this is the definition of a Boltzmann measure. So it's simply a law where we take a Boltzmann weight T to the power of volume, nu to the power of number of monochromatic edges. And now this TC is, it's a critical value depending on mu. So it's on the critical line, this point. And we normalize it by the partition function. And here's a concrete example from the last page. So this is not really useful. So we don't really know what this Z34 is. We know it much better at the limit when P and Q tends to infinity by the asymptotics we just showed. All right, so let's use it. So we need first some definitions. So we need to define how do we take limits, and what is easiest is to take local limits. What means that we define first a local distance between two triangulations with Ising spins. So as usually, two triangulations or two maps are close with each other locally. If you can find a large ball with large radius where those two triangulations agree, okay. So, but we want, moreover, we want that inside each ball of radius r, the two maps, the spin configurations would also agree. And the larger radius we can choose, the closer the maps are to each other. So eventually, if the maps are the same, we could choose infinitely large radius. So in any ball. Okay. So this definition is classical, except it takes into account the colors in the faces or vertices. Okay. So then we can in fact show that these Boltzmann distributions converge weakly with respect to the local distance, which we just defined. So we can take the local limit in two different ways. Either we let first the minus boundary tend to infinity, and after that the plus boundary tend to infinity, or we could let the plus minus boundary tend to infinity simultaneously. And this is simply using the asymptotics we just showed in the previous theorem. And what this means that we find explicit probability distributions, or which are supported on triangulations of a half plane actually. So here we have already an infinite boundary, and same here. And then moreover, like these local limits, they would be one-ended, so they're really triangulations of half plane. So it means that if we take away any finite subgraph, the complement would be still infinite and would only have one connected component. Except when we are in the low temperature, in fact, this local limit would create a bottleneck. So it means that it's not really a triangulation of a half plane. So we could take a finite bottleneck away, which disconnects the map into two infinite components. So this is something I will talk more slightly later. So let me show the idea how we show this result. So we go back to our combinatorial decomposition, which is in combinatorics called Touch equation, but in the probability side, it's more or less the first step of a peeling process. So what does a peeling process mean? So we simply define a set of events which correspond to now the locations or the how this triangle looks like, what we reveal here. Okay. So now I chose to peel from the minus edge instead. But it doesn't really make big difference which one we choose. Okay, so if we peel from the minus edge or anything here, we find formally we write location of this endpoint. So it's either center plus or center minus, depending on the spin of the triangle which we encounter here, or it's located on the left or on the right, etc. So we just encode these events like this. And as I mentioned, we can view it as a distribution of the first peeling step in the peeling process of the Boltzmann triangulation. So recall that Boltzmann triangulation would be random. So then it's a random triangle with a fixed boundary length. Well, now the question is, how does the boundary evolve in this type of operation? Well, first of all, we can show that all those peeling steps, they converge when we let P and Q tend to infinity. We find explicit probability distributions on those limit events. Then we just iterate this in the limit to obtain explored and unexplored map, which have random boundary length. And that random boundary length or random perimeter turns out to be a Markovian process, Markov chain, more or less in 2D. And moreover, we can keep track on how the boundary changes. So in the finite boundary case, we simply look how much the boundary differs from its initial state, which is PQ. Okay, and we can also actually define it in the infinite setting because we just like look how much the boundary changes starting from the first step in this exploration. Okay. So here's a picture. So let's imagine on the left that we have started from next to this root and we have explored this peeling process n times. So we have found an explored triangulation with some random boundary length. And then there's an unexplored map. So then we continue. So one notable thing is that this Dobrushin boundary conditions allows us to, like, it's always stable in this peeling operation when we define it in the correct way. So there will be always a Dobrushin boundary, and when we reveal the triangle adjacent to this edge here, for example, in this case, okay, we find a triangle which splits it in two parts, and then we just we need a rule to fill in one of those parts, such that we are again in the same situation, that we have an unexplored simple part here, and then we reveal a triangle here. So this is a way to recursively explore random triangulation. Okay, and it's a Markovian way in the sense that the law of this area would always stay the same with just new boundary length. So this is called spatial Markov property. So this is very nice because we can actually show limit distributions for many things. So one particular case is that if we look at the critical point, which is in many sense the most interesting, Then the parameter fluctuations, actually, they are in the domain of attraction of a stable distribution of exponent 4 over 3, which is very well known in the literature of Liouville quantum gravity, for example. So if we look at this rescaled parameter fluctuations by this n over 3 to the 3 over 4 factor, we find an explicit scaling limit in distribution with respect to Skorokhod topology. So there are random Cadillac functions, which are actually independent spectrally negative stable processes with exponent 4 over 3. And they have some very explicit Levy measures where actually these coefficients here, they are not the same when the spins are on phases. And that was simply because the peeling process itself is asymmetric. So we all the time peel from a minus edge or a plus edge. But if the spins are on the vertices, there is more symmetry, then actually these two coefficients are the same. Well, okay, but then how does the phase transition look informally? So first, if we look at the high temperature, we would get the picture with a lot of disorder, which is actually expected in high temperature Ising model. So there would be a percolation-like thing, and more precisely, it would correspond to subcritical percolation in the phases. Okay. Well, in the low temperature, there would be a finite bottleneck of the surface, and indeed, we could find that almost surely the interface between this minus and plus cluster have a finite length. And that's the reason is that somehow the low temperature Ising model, when it interacts with the random discretization of the sphere, it forces the bottleneck to hold. So this is something which is also predicted in physics literature, but it's not really commonly written anywhere. Okay. Well, but what happens at the critical point? Then again, we find local limits, which are really triangulation of the half plane. Here, there would still be infinite spin clusters, so infinite minus and plus cluster. But then there's an interface between those two clusters, which is somehow has a non-trivial scaling property. So our core thing to show in the critical point is basically there are many things related to this interface. For example, it only hits the boundary of the half plane a finite number of times. So that's why it turns out that it will actually drift to infinity. So here on the high temperature, the interface would just bounce back to the boundary infinitely many times. Okay. So then what is kind of the key thing is to understand how this boundary evolves in the peeling process. That's something we put a lot of effort, and that's really technical in many parts. Okay, well, we can also look at the case when we have still a finite plus boundary. Then we would, if let's say we have a large plus boundary, we would have a large plus cluster here adjacent to the boundary. And it's a good question to study also, how does the interface of this behave? Well, this question we answered to some extent. So, okay, let me first show another picture. So recall that in the interface between spin clusters, simply just the domain wall between those two. So here in the picture, it's red here is a finite cluster and finite interface. Finite interface between a finite cluster and infinite cluster. Here also, when we are on the finite triangulation of a disk, the interface separates two finite clusters. But in the half plane, it could also separate, well, it could be infinite. Well, when the spins are on phases, one should note that actually there are several interfaces. It's not only a single curve, but there's like a family of curves which we call a ribbon in our work. But if we put the spins on the vertices, we would have unique interface curves, which is somewhat nicer. And all right, so what can we say about these interfaces? So if we look at this picture B here, where we have still a finite plus boundary, then we would have, let's say, we call the interface length eta p, which is now between two marked boundary vertices at the junctions of these points where the interface change. And we found an explicit scaling limit first for the spins on faces, except it's not exactly the interface because there are many interfaces, and there are some other technicalities. But when the spins are on vertices later on, I could show that in fact we find a scaling limit of this interface length in the following sense. So when we look at this length and rescale it by p, which means that the interface length should roughly scale like the plus boundary length. It has an explicit limit distribution, and I will tell a few words about this in the next slide. But we can also take this scaling limit simultaneously such that the plus and minus boundary tend to infinity. So if we go one slide back, we just look this plus and minus from the disk and look at this interface length when spins are on the vertices, so that we have a unique curve, and then let p and q tend to infinity and rescale by the length of, say, plus boundary. So we find this type of integral formula, which is slightly more complicated than this one here. But if we let this q and p tend to infinity at the exactly same rate, then we would find equally simple formula, but slightly different exponent. Well, why is this exponent 4 over 3 here, which actually looks pretty much like the critical exponent in the asymptotics? This is a miracle. I mean, so far we don't have a combinatorial explanation for this, but this is nevertheless predicted in physics literature. So, for example, in the literature about O and loop models, this occurs somewhere, and it has also an interpretation in Liouville Quantum Gravity, which has been shown really recently. So this is something, if you don't know about it, don't worry. It's just about to give you some idea that this really exists in a continuum. So if we look at two quantum disks in Liouville quantum gravity theory with a parameter square root of 3, which was extensively studied by Duplantier, Miller, and Sheffield via the mating of trees thing. Then if we condition these two parameters to be, let's say, 1 plus L and L plus lambda, so L is now the length of the interface, and conformally weld two quantum disks in this theory, which was recently done by Maurice Ang, Nina Holden, and Xin Sun. And then we sampled the interface length from a from a 2D Levy measure, conditionally on this boundary length of the disks. Then this gives a limit law of L, which actually coincides with the scaling limit we just showed. And moreover, if we similarly, if we glue a quantum disk with a quantum half plane or so-called thick quantum wedge, we would find the same limit law. So they really seem to coincide with Liouville quantum gravity, which is conjectured to be the limit of this critical Ising model. All right. Finally, let me mention that the idea to use rational parametrizations together with singularity analysis, it has been used also by other authors afterwards. So there's last year, Marie Alban and Laurent Menard applied similar idea to study the clusters size of the Ising model on full plane triangulations, so without boundary. And they can, for example, take finite clusters and study the boundary length per meter of finite cluster, and they would see that they actually how they scale, and in particular in the high temperature region they were able to show that they converge in the scaling limit to stable loop trees of parameter 3/2. So their approach used rational parametrizations which look really similar than ours. Okay, and how could we explain this Ising universal class? This is an ongoing work. What I've been thinking with Jérémy Boutier and Grégory Mermont. So we are more precisely studying Owen loop model on random triangulations with a boundary. And what is this Owen loop model exactly? So the idea is that we can again take a triangulation of a disk, and then we put a loop configuration on it, which means that its triangle either it carries a piece of loop or not, and its triangle which carries a piece of loop gets a weight h, and its empty triangle gets a weight g. Okay, but then moreover, if we have a closed loop, its closed loop carries a weight n, and then open loops which cross the boundary have weight 1. Okay, so they don't carry this weight n. Okay, so now the critical Ising model, what I was discussing, would correspond really roughly to the n equals 1 in the dilute phase of these parameter values, which I won't explain now, but I would be happy to discuss more if you're interested. Okay, and yeah, so our ongoing program is to understand this type of questions better, and we have several research directions in this. But one thing which we should mention is that the existence of those rational parametrizations of generating functions don't hold for all those values n. So they actually hold only for some very special values. For example, this n equals 1. So this would give percolation in the dense phase, for example. And there you could also find rational parametrizations. But you could find values of n where it's hopeless to try to find rational parametrizations. So we would need to consider different type of parametrizations. Okay. All right. Then finally, I mentioned a few works in progress, and future directions. So first, what we have been doing with Linxiao is that we have been studying so-called near critical regime, where we can let the temperature tend to a critical one. So we don't keep it as a constant as we did in the previous works, but we could, for example, look how these spin clusters scale when we let the temperature nu tend to critical one at some prescribed rate together with the boundary tending to infinity. Let's say we could find the scaling limit of a boundary also in this way. Well, then also I've been thinking about more general boundary conditions where, for example, we could add like 4 boundary segments and look at the crossing probabilities of the interfaces. So expect some sort of Cardis formulas pop up there. And there are even more exotic boundary conditions, which have been also studied in the case of the loop models with Jérémy and Grégory. And what is also a long-standing program in the field is to find arguments towards universality, that actually these things shouldn't be too much lattice dependent. But so far we are still restricted to study these simple cases like triangulations and quadrangulations and so on. This is more like future direction. And then there are many other simple questions related to scaling limits of volumes and perimeters and so on. And finally, which is a big goal in the field, is to understand the scaling limits of the interface and about volumes as well with a conformal structure, which would correspond to the Liouville quantum gravity plus Stram-Liouville evolution setting. And really finally show the scaling full convergence of this model with a conformal structure to a Liouville quantum gravity surface. So that's a big goal in the field. So there will be many ways to contribute if you're interested in this kind of questions. So I'm done. Thanks for your attention.
Thank you very much.
Thank you very much.
Thank you. Thank you for the nice talk. So maybe I will start with the question that might break the ice. So it's related to the slide in which you have shown the bottleneck of a finite width.
Yes.
And okay, so you have this. Yes, precisely. So you have these local limits.
Yeah.
And then, I mean, a natural question is about the rigidity of the interface. Do you have any idea on the rigidity of this interface in the DFS? I mean, can you develop about?
Could you recall what do you mean by rigidity of interface?
So I guess that this interface will fluctuate. And the question is, what is the order of magnitude of these fluctuations?
Well, I mean, yes. So at the critical point, I guess it could be given by this, right? So this gives more or less the fluctuation of the interface length. Okay.
Okay. I see.
So it would be scale like for a tree stable process limit. So it's related to those Ramp-Learner evolution curves as well. Yes. These are the critical point. Well, it's more trivial in somehow. Okay, it's a good question actually. So if let's say that we have spins on the vertices like in this picture, then we expect that in the high temperature this should correspond to a SLE6 curve, like which is the same for critical percolation. So it would behave like a percolation. Okay. So that's a good question, and indeed it's an open research question what you will just ask. And well, in this case, well, it should just be a straight line more or less in the scaling limit. So it's but indeed the length of the bottleneck and its distribution, maybe there could be things to show about it. But so far what we just used is that okay, the bottleneck has a almost surely finite length, and so yeah.
Okay, thank you. So are there other questions?
Maybe just the table where we added, you said that it's surprised that it's the summation of, yes, this one.
Yeah, well, it's kind of not surprise if you think about the geometric intuition, like, but rigorously speaking, it's not that easy to say if it has a combinatorial interpretation or not. But in fact, like certain values are important. For example, here in the low temperature, the fact that this alpha 0 and alpha 1 are the same, it's actually basically what gives the bottleneck in the limit. So you basically glue two like triangulations with the monochromatic boundary to each other. And then later on, if we go more refined study to the spin clusters, then this would make more sense, this alpha 2 also. But it's not really straightforward why these sum to each other.
Yeah, thank you.
Okay, other questions? Okay, if not, let's thank again the speaker.
Thank you very much.
And I recall that this video will be available on YouTube. So if you have further questions, don't hesitate to put them in the comments. So okay, we are closing for today. We will restart in 2 weeks with the next contribution for this current thematic season on probability and statistical mechanics. Thank you very much. Thank you, Joonas, for your contribution, and have a nice afternoon, everybody.
Have a nice
You too,
afternoon.
thanks.
Thank
you.
you.
Thank you.